So welcome back. Today we'll discuss the problem number 4. Here the beam with fixed end, and there are two similarly supported at a distance of 4 meters from the left, and the base is also 4 meter, an UDL of 20 km per meter, and we do have a moment 100 km per meter, 100 km meter at the point 2 meter from the A. For this beam, the kinematic indeterminacy is equal to 2. We have two unknowns to solve. That is, two rotations are possible at point B and point C, which is the kinematic indeterminacy. So this will be the global coordinate 1, 2, 3, 4, 5, 6, 7, 8, 9 for A, B, and C. And in this one, the kinematic degrees of freedom will be 6 and 9. All other displacement will be 0. Even for the left one, the 3 will be 0 as is a fixed end moment. So fixed end. In this problem, local coordinates and global coordinates are parallel because taking individually AB, individually BC, the local coordinates are equal to the global coordinates. So we don't need to change from the local to global. It will happen only for the portal frames and some inclined frames. All the beams will be purely horizontal, and no need to worry on that. So the connectivity for the member 1 is between A and B, node 1 and node 2. For the member 2, this 2 and 3. And for the member A, you have local degrees of freedom is 6. Same thing for the global degrees of freedom 6. For the member 2, it will be at the junction. It is 3 and 6 will be there, and in global coordinate it is actually 6 and 9 if you relate with the global and the local coordinates. The member stiffness metrics of a 2D frame member in local coordinate are given for the SMI is equal to, for a single element, is equal to EA by L into all the values are known to you. Now we know that for the member 1, for the member 1 only 6 will be there, and all other value U1, U2, U3, U4, U5 will be 0. Hence the corresponding value will be the last one for EA by L, will be the stiffness matrix, element stiffness matrix for the member 1. And for the member 2, we have 2 degrees of freedom, right? 3 and 6. So the corresponding 3 and 6 has to be taken. All other column and rows will be cancelled. So 3, this one, 6. Here also 3, here also 6. So taking 1, 2, 3, 4 values out to get the value of SM2. Now we have actually the rotation matrix will be 1 only because there is no theta value, theta is equal to 0. So on substitution, we'll get the corresponding 6 value as 1. So there is equal to 1. For member 2 also the theta is equal to 0. That will be 3, 6. So 1, 0, 0, 1, 1, 0, 0, 1. There is no need of transformation because local coordinate and the global coordinate are parallel here. And we have the member stiffness matrix in global coordinate given by SM S1 is in the actually structure. Global coordinate is equal to the local coordinate is equal to EI, global degree of freedom 6 for the member 1. And for the member 2, SM S2 is equal to SM2 is equal to EA by 2 into 2, 1, 1, 2, 6, 9. Assembled and reduced global degrees of freedom. So upon adding both, because for this member we have 6, right? 6 plus 3 will be added, and this 6 will be as such. So there will be addition at this point, the 3 plus 6, 2 plus 2, 1, 2, 1, 1, 2. the SJJ inverse is equal to inverse of this matrix will be 2 by 7 EI into 2 minus 1 minus 1 4. So now we obtained the SJJ minus inverse, and we have the fifth one, loads. So we are supposed to convert the loads into the equivalent joint loads, as the loads are not acting at the joints. So now we are very well known about how to convert for the moment and well as the UDL. So not going much into that part. So the equivalent joint load obtained will be the AJ is equal to minus 1.67 and 26.67 for the corresponding kinematic degrees of freedoms. The joint displacement dj is equal to sjj inverse into aj is equal to 2 by 7 ei into 2 minus 1 minus 1 4, which we have obtained just now, and into minus 1.67 26.67 will give you the value 1 by ei into minus 8.574 30.957. Then the member end action AMI is equal to AMFI plus SMI into RT into D global. So AMFI has a value because it's a fixed end action. So for the member one, the value will be minus 25 plus EI into 1 by EI into minus 8.574 is equal to minus 33.574. For the member 2, we have the fixed end actions given by 26.67 here and 27.67 here, plus EI by 2 into 2 2 into 1 by EI into minus 8.574 30.957 to obtain 33.5790. So this will be the member end moments. Quickly into the problem 5. Here also the procedure will be almost same. Only thing is that you have one less degrees of freedom, because here also A and C is restrained, only B is there. So only you have to account for DF1. Okay, and this has to be converted to the equivalent joint load, and then 12 also has to be converted to equivalent joint load. Those things will be the routine work. So Ki is equal to 1, rotation B, global degrees of freedom and the local degrees of freedom are both same. The connectivity you can write down, and you know that only if you write for the 1 2 3 for the local coordinate, here also 4 5 6, then again 1 2 3 and 4 5 6 for the second element. For the global coordinate 1 2 3, then 4 5 6 7 8 9 will come. So the sixth one will be the rotation, and only sixth one will be remaining. So for the member one, local degree of freedom 6 6 will come, and for the member 2, here local coordinate will be 1 2 3, so third one will be rotation. So third in the local coordinate and the corresponding coordinate in the global will be 6. So is equal to SMT is equal to 4A by L into is equal to 4A by L is equal to 0.4 into EA. Here also there is no rotation matrix required. The value, the local coordinate and the global coordinate are same, and hence the member stiffness matrix in the global coordinate is equal to same as 0.4 EI. And also for S2 is equal to 0.4 EI. Then the next phase is assembled and reduced global stiffness matrix. We have to club the values both SMS1 plus SMS2, as both the rotations are happening for member 1 and member 2 combined in the rotation for the B. So just adding 0.4 plus 0.4, 0.8 into EA. SJJ inverse is equal to 1 by 0.8 EA, and hence the fixed actions can be computed directly, and the equivalent joints loads are written. So the AJ is equal to 15 here, And joint displacement, we have the equation dj is equal to sjj inverse into ajc is equal to 1 by 0.8 ei into 50 is equal to 18.75 by ei. Then the member end action AMI is equal to AMFI plus SM into RT into D global. So for the member one, we have the fixed end moment as 30 minus 30 plus 0.4 EI into 18.75 by E is equal to minus 22.5. For the member 2, we have the value as 15. So 15 plus 0.4 into A into 18.75 by A is equal to 22.5. And the member n moments are obtained, and it is actually drawn in the figure 32.5 and 32.5 in the corresponding directions. Okay, so this will be tedious part because the local coordinate and the global coordinate are never same because that you need rotation matrix. So obviously for the beams, BC will have the same thing. BC will have local coordinate and the global coordinate same. Because there is no rotations required. It is actually theta is equal to 0 degree. But for the column, it is actually theta is equal to 90 degree. So those changes will be applied. And now we are focusing on the global coordinate will be 1, 2, 3, 4, 5, 6 and 7, 8, 9 at the node 1, 2 and 3 respectively. There are two elements, one is a column element and one is a beam element. And the connectivity is written here, member 1 connect 1 and 2 node, 2 connect 2 and 3. Here degrees of freedom, there the kinematic indeterminacy we have, there is no rotation, vertical horizontal movement at A, there is no vertical horizontal movement at C, only rotation is for C, so one is the 1 degree of freedom here. Then B also can have the rotation, so the 6th one rotation and the 9th one rotation will be the degrees of freedom. The degrees of freedom in the local coordinate are also written. So 1, 2, 3, 4, 5, 6 will be for the first element, and repeatedly 1, 2, 3, 4, 5, 6 will be for the second element also. So the corresponding degrees of freedom, if you equate local degrees of freedom for the first element will be the 6th one, and in global also it is 6. For the member 2, it will be 3 in the local coordinate, correspondingly 6 in the global coordinate, and 6 in the local coordinate and correspondingly 9 in the global coordinate. So those are written here. Then the member stiffness matrix of a 2D frame member local coordinate for the member 1 and member 2 are written. And we have isolated the 6th and 9th one. There is actually the 6th and the, for the member 1 only 6 is required, member 2 3 and 6 is required. So this is actually corresponding, this square is for the member 1 and these oval shapes are for the member 2. So member 1 will have the 6 degrees of freedom for A by L. This value is equal to EA into 1 is equal to EA. For member 2 we have the matrix. It is picking up these values 1, 2, 3 and 4. I give you this is equal to EA 0.5 into EA, 0.5 into EA. Then the rotation transformation matrix, you know, for the member 1 is a column element, theta is equal to 90 degree. So you need only the last coordinate, right? 1 will be there, so it will be same as RT1 is equal to 1. For the member 2, theta is equal to 0. Upon applying, you will get the value 1, 0, 0, 1. It is 3, 6 degrees of freedom. Okay. There is no need of transformation because the local coordinate and the global coordinate are parallel. So actually for the column, the rotation matrix is equal to 1 because it is actually the moment, not the x and y. The x and y will definitely change as it's a column member. The moments will be always in a direction, right? So there is no change in the local coordinate and the global coordinate in the case of moments. And in RT2, it will be 1001. As you know, it is actually the beam local coordinate and the global coordinate are same, corresponding to the local degrees of freedom and 3 and 6. The member stiffness matrix in global coordinate transform member stiffness matrix SM S1 is equal to EI and SM S2 is equal to EI 0.5 EI 0.5 EI EI. For assembled and reduced global stiffness matrix, we have the clubbing with the 1 and 2. So this joint thing EI will be clubbed is equal to EI into 2.5 0.51. Then we have the loads coming as 20. It's still joint, so there is no need to convert it into the equivalent joint load method. 10 has to be transformed, and upon transforming, the beam will have the corresponding values, and the equivalent joint loads are marked here, and the 20 is applied as such. So combined loading will be the equivalent joint load plus the actual joint load, and this will be the fixed and action moment. So load corresponding to 6 and 9 will be minus 13.33 being anti-clockwise and 13.33 being clockwise here, fixed and moments. Now we have the equation dj is equal to sjj inverse into aj is equal to 1 by EI into minus 11.43, 19.04. And for the member and actions, you need to add also the moment, fixed and moment. AM I is equal to AMFI plus SMI into RTI into D global. AMFI is equal to fixed and actions of member I. For the member one, actually there is no load other than at the joint, so the fixed moment is 0. Plus the corresponding values are put to find minus 11.43 as the AM1. So this is a member end action corresponding to the local degrees of freedom 6 in member 1. There is a member end moment at the top edge of the member 1. For the AM2, definitely there is two fixed end moment, which will be 13.33 and 13.33, which is written here, and then it is clubbed with the equation to get 11.42. So these are the member end actions corresponding to local degrees of freedom 3 and 6 of member 2. That is member end moment of member 2. So the values are written here for member 1 and member 2. Okay. Now once you are okay with the previous one, the other problem will be just a revision of the procedure. So here the main difference is you have a 2 column and 1 beam, and this 60 has to be converted to the equivalent joint load, this 30 has to be converted to the equivalent joint load, and definitely there will be 3 degrees of freedom, 2 degrees of freedom, one rotation here, one rotation here, and also there will be one more because of the side sway. So the quantity will be member 1, member 2, member 3 between the different nodes. E is a constant. This value is 3 meter. This is 3 meter. Totally 6 meter. 6 meters length of the beam. 30 km per meter is the UDL and 60 km is the horizontal load. So you need to know that there will be 2 rotation degrees of freedom. Additionally, there will be one translation also, which is actually 4, 6 and 9. So the displacement in the global coordinates are written here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And for the local coordinate again now 1, 2, 3, 4, 5, 6. Then again 1, 2, 3, 4, 5, 6. Then again 1, 2, 3, 4, 5, 6. So the kinematic determinacy GDOF is equal to 4, 6 and 9 will be the values. There will be some displacement values. So these are the explained degrees of freedom and the local coordinates. So the full matrix will be 1, 2, 3, 4, 5, 6 for the individual element stiffness matrix. The member stiffness matrix of a 2D frame. Member is local coordinate is written here, and we need for the member 1, 2, 3. The member stiffness matrix with local coordinate which are constantly in the restrained degrees of freedom. So SM1 is equal to SM2 is equal to SM3 will be an ideal matrix of this. Then again, the rotation matrix for the first element, for the first member, RT is equal to given as in the matrix. Then RT1, theta is equal to 90 degree. So corresponding changes will be there. Second one will be the beam, so theta is equal to 0 degree, and the third one will be the column. So the measurement with the horizon will be negative, so minus 90 degree. Then S1 is equal to RT1 transpose into SM1 into RT1. So the full matrix is written here. Here actually the initial reduction in the matrix is not done. We are writing it as a individually for the different elements, and later we will club it. Okay. So SM1 is directly found as RT1 transpose into SM1 into RT1. There is a stiffness matrix in the global coordinates. So it's obtained as detailed 1, 2, 3, 4, 5, 6 global degrees of freedom. And for similarly for the member 2, RT2 transpose into SM2 into RT2, it's obtained the value as this. SM3 will be RT3 transpose into SM3 into RT3. So getting the value as this. Now we are supposed to assemble it. Okay, now we are going to assemble where the common degrees of freedoms are shared. So we know that the 4, 5, 6, 7, 8, 9. That is in the global degrees of freedom, you know 1, 2, 3 will be 0, 10, 11, 12 will be 0, 4, 5, 6 will be there, then again 7, 8, 9 will be there. So only these coordinates are taken in the global coordinate. So the corresponding matrix is written here. 4, 5, 6, 7, 8, 9. Okay, so add the different element contribution accordingly to get this bit matrix, and then now we know that the values 4, 6 and 9, that is 4 will be the horizontal deformation, 6 will be the rotation, and 9 the rotation will be there. All the other values can be made to 0. So all the rows and columns corresponding to 5, 7 and 8 can be cancelled to get a 3 by 3 matrix. 4, 6, 9. So this will be the matrix. Then neglecting the axial deformation SJJ can be further reduced to 4, 6, 9. That is such an assumption. Okay, so that is actually EA will be the axial deformation. If you neglect it, this term will be 0. So 12EA by 6 cube, then other things will be same. So again, simplifying and applying the values, you get the EA by 36 into this matrix. So actually it's your choice whether to neglect the EA or not. So it's up to you. So here store that is neglecting in the analysis, and so the values are cancelled, values are not accounted. Then the loads, so in the problem you know that there will be equivalent loads for the member AB as well as BC, and CD has no load. Okay, so the member AB will have the equivalent joint load, the BC will have equivalent joint load, and CD nothing will be there as fixed action. Then equivalent joint load is also written there, combining with the real action loads. So load corresponding to 4, 6 and 9 will be 30 will be horizontal one, 45 will be clockwise so negative, and 90 will be anti-clockwise so positive. Then the joint displacements can be found. dj is equal to sjj inverse into aj is equal to 36 by a into 260 648 12. So all those things are taken from the previous calculations to get 1 by a into 1170 minus 210 120. Then the member actions, so which note that it will be the fixed moment will be coming. So the fixed value will be 0, 30 minus 45 for the first member. Here 30 and 45 will also there, right? So those things are there, and getting value member 1 as 0, 0, 10. These are the member and actions corresponding to the local degrees of freedom 4, 5, 6 in the member 1. Similarly, for the member 2 also you have to find. So the fixed moment will be 90 and minus 90. So it will be 90 and the minus 90. Then again simplifying, minus 10, minus 80. Member 3 also, if the right column don't have any load, so the fixed moment will be 0. To get the values 80. Then the member moments are obtained values are plotted and solved. So this problem we can solve as a homework. No, actually this is actually a same as the previous problem with a simplified approach. So we'll see what's the difference in this one. Here the problem question is written here, quantity is written here. So the global coordinates and the kinematic coordinates are written here. So the degrees of freedom and local coordinates are written here. This thing is up to this point is the same. Then again the member stiffness matrix in the element coordinate are written here. Then here the constraints are taken from the member 1 itself. That's the main thing. In the previous problem, we didn't take the constraint initially. After making the matrix, then we have in the addition we have cancelled the different. We have imposed the boundary condition. So here itself the 4, 5, 6, that is actually 1, 2, 3 will be the fixed end, right? 1, 2, 3 will be the fixed end, so there will be no value. 4, 5, 6 will be the value. So only the yeah, 4, 5, 6 will have some value. It is written there. From this matrix, only the 4, 5, 6. So only this value is taken. This value means, and yeah, this value is taken, which will be corresponding to 4, 5, and 6. This will be 4, 5, 6. All other values will be cancelled. This will be cancelled. Okay. All others will be cancelled. This box will be taken. And for the member 2, the local degrees of freedom are 3 and 6. So that means it is the rotations for the local coordinate, right? Because member 2 will be the beam. Beam will have left side 1, 2, 3, right side 4, 5, 6. 3 and 6 will be the rotation, and that value is only taken to get the matrix is equal to A by 3 into 2, 1, 1, 2. For the member 3, that is for the rightmost point, we have only rotation happening. So that 1, 2, 3 will be there. 3 will be the rotation for the member. That is in the local coordinate. It is this one. Yeah. So this will be for the last one member. Sorry. Okay. So the local coordinate will be 3 and the global will be 9. So to get the value, in case transformation is automatically done, as a local DOF is chosen corresponding to the global degrees of freedom. So we are adding it in the global level. We don't need to convert it so directly. We are taking the SM S1 will be 4 and 6, and SM S2 will be 6 and 9. That is in the global degrees of freedom and 9. So only we are assembling in the global level. 4, 6, 9, getting the value as EA by 36 into 260, 648, 12, 0, 12, 48. It's the same as in the previous approach. And then the procedure will be same, the load calculations, getting the current joint load, joint displacement, member and actions, member 2, member 3, member and moments, all the values will be same as it. So these problems you can do in homework. The only thing is it's actually in a different unit, 0.24 gives per inch. Some load is there, so we have to convert it to the equivalent joint loads. Then the angle has to be taken properly for the rotation metrics. Here the local coordinate and the global coordinates are written as slides 1 and 2. Then the 3 degrees of freedom will be the rotation. So the both A and C will be fixed. So only rotations and displacement will be there for the B, which will be the 4, 5, 6 will be the degrees of freedom. So you can take that but assemble it in an order to get the values, and you can repeat for the problem 9 also, same procedure. This will be a truss one which you have solved in the problem 1 and 2. So those metrics has to be remembered. You have to give for the rotation metrics, you have to give for the element stiffness metrics, and properly club it to get the global stiffness metrics, then reduce it. So that's the type of problems you will be facing in module 4. Okay, thank you.